Okay, hello, welcome back to AMT 151 Basic Electricity. Um, Please type in the chat if you can hear me. I think that I may have fixed the microphone issue that I've been having for a long time. So hopefully this lecture will sound a little bit better. I know we only have like a few weeks left in the semester, but today we're going to talk more about inductance and inductive reactance. I know that last week in the last lecture I had posted a few videos for you guys to watch, and hopefully those were helpful as far as the examples that were used. And today we'll go over some of what some slides, just some more definition and laws, and we will finish up our discussion on inductance and inductive reactance. So okay, good. I'm glad you guys can hear me. So I'm going to get started as usual. You guys can type in the chat if you have any questions, or if I'm going too fast, or if you need to see another slide. I'm trying to plug in my laptop here so it doesn't die. Okay, so today we'll be talking about inductance. Oops. We will go over characteristics of inductance, the RL time constant, physical parameters of inductance, self-inductance, what self-inductance is, types of inductors, units of inductance, and inductive reactance. Characteristics of inductance. Michael Faraday. He discovered that by moving a magnet through a coil of wire, a voltage was induced across the coil. The amount of induced voltage is directly proportional to the rate of change of the magnetic field with respect to the coil. Faraday's law, sometimes also called the law of electromagnetic induction. This states that the induced EMF in a closed loop of wire is proportional to the rate of change of the magnetic flux through a coil of wire. The primary aspect of the operation of a coil is its property to oppose any change in current through it. This property is called inductance. Induced voltage is always in the direction opposite to the direction of the current flow. The effects of this countering EMF are to oppose the immediate establishment of the maximum current. This effect is only a temporary condition. Once the current reaches a steady value in the conductor, the lines of magnetic force no longer expand and the countering EMF is no longer present. There's a little more definition of these properties with the counter EMF in your textbook, so I would recommend reading up on that to get a better understanding of how that works. The RL time constant. So the inductor's basic action is to oppose a change in its current. The current cannot change instantaneously in the inductor. A certain time is required for the current to make a change from one value to another. The rate at which the current changes is determined by a time constant, and this is represented by the Greek letter T or theta. The time constant for the RL circuit is T or theta equals L over R. This is where T or theta is defined as seconds. L is our symbol for inductance, which is measured in henries. That's what this H is, the capital H. So L is our representation for inductance. H is our units of measurement, henries. And R being resistance, which is measured in ohms. I left out a parentheses there. And this is a handy little chart that comes from your textbook, the 8083. Gives a representation of some current, counter EMF, and applied voltage in inductive circuits. So in a series RL circuit, the current increases to 63% of its full value in one time constant after the circuit is closed. That is what this diagram explains. Okay, so we have one time constant right here. We have 63% of the current right here. And our applied voltage and counter EMF. This buildup is like the buildup of voltage in a capacitor when charging an RC circuit. Both follow an exponential curve and reach 99% value after the fifth time constant. Okay, so that's just a little bit of information on the RL time constant. You don't need to know a whole bunch of detail for that as far as the FAA is concerned. Just some further information on inductance and the RL time constant. Physical parameters, physical factors affecting inductance. Number one, there's 4 factors affecting inductance. Number one, the number of turns. Doubling the number of turns in a coil produces a field twice as strong if the same current is used. Okay, so number one factor affecting inductance is the number of turns in the coil. Number 2, the cross-sectional area of the coil. The inductance of a coil increases directly as the cross-sectional area of the core increases. Doubling the radius of a coil increases the inductance by a factor of 4. Number 3, the length of a coil. Doubling the length of a coil while keeping the same number of turns halves the value of the inductance. And number 4, the core material around which the coil is formed. Coils are wound on either magnetic or non-magnetic materials. Non-magnetic materials include air, copper, plastic, and glass. Magnetic materials include nickel, iron, steel, or cobalt. Magnetic material have a permeability that provides a better path for the magnetic lines of force and permit a stronger magnetic field. Self-inductance. Lenz's law. This law is summarized by a German physicist named Heinrich Lenz. This was in 1833. Lenz's law states that the EMF induced in an electric circuit always acts in such a direction that the current it drives around a closed circuit produces a magnetic field which opposes the change in magnetic flux. Okay, so a very wordy law. Give that a read a couple of times to wrap your mind around it. That's Lenz's law. Self-inductance is the generation of a voltage in an electric circuit by a changing current in the same circuit. When the current in a conductor changes direction, there is a corresponding change in the polarity of the magnetic field around the conductor. Okay, change in polarity. This makes a changing current produce a changing magnetic field around the wire. To further intensify the magnetic field, the wire can be rolled into a coil called an inductor. The changing magnetic field around the inductor induces a voltage across the coil. This induced EMF is called self-inductance and tends to oppose any change in current within the circuit. This property is usually called inductance and is symbolized with the letter L, capital L. Units of inductance. We've talked about this a couple of times. I believe it was mentioned in the videos from your last lecture. But we measure inductance in henries, which is a capital H. The henry is the basic unit of inductance and is symbolized with the letter capital H. An electric circuit has an inductance of 1 henry. When current changing at the rate of 1 ampere per second induces a voltage of 1 volt into the circuit. In many practical applications, millihenries and microhenries are more common units. I don't think I have a figure for you guys. Okay, so often you will see millihenry and microhenry, which remember is symbolized by a lowercase m and a capital H is millihenry, and your microhenries is this symbol kind of like a U for micro, and your capital H, microhenries. Okay. Inductance is measured in henries. Types of inductors. Here's your schematic symbol for an inductor. It's a drawing of your coil. You will see this symbol, I should have put another symbol up here, but you'll see this symbol, you know, this like a circle-y wire, and sometimes you'll just see these little like bumps without these circle-y, well here, I guess I could look it up instead of describe it. I actually think there's an example in your book. Here. So you have these, instead of these like circle-y wire schematic diagram, you can also have these like multiple like little humps right here. So that's also your symbol for inductor. Values of inductors range from nanohenries to tens of henries. So can be very, very small, can be very, very large. Inductors are classified by the type of core and the method of winding of them. The number of turns in the inductor winding and the core material determine the capacity of the inductor. Okay, so that determines the capacity of your inductor, the number of turns in the inductor winding and the core material. The core material is usually the most important aspect of the inductor's construction. Cores made of dielectric material like ceramics, wood, and paper provide small amounts of stored energy, while cores made of ferrite substances or magnetic substances, when I say ferrite, that means magnetic, substances have a much higher degree of stored energy. Most common core materials are air, solid ferrite, powdered ferrite, steel, toroid, or ferrite toroid. Those are the most common. So talking about inductive reactance. What's the difference between inductive reactance and inductance? Well, here we have our inductive reactance is a measure of how much the countering EMF in the circuit opposes current variations. Inductive reactance is symbolized by capital X and L, XL. And inductive reactance is measured in ohms. Inductance is defined as the property of a circuit to oppose any change in current. Inductance is measured in henries, capital H. The inductive reactance of a component is directly proportional to the inductance of the component and the applied frequency to the circuit. Increasing either the inductance or applied frequency will result in an increase to the inductive reactance and increase opposition to the current in the circuit. So what's our formula for inductive reactance? I think hopefully you guys went over that video from the last lecture, and I believe it had a few examples of using this formula. But our formula for inductive reactance is XL equals 2 pi FL. This is where XL is the inductive reactance measured in ohms. Our lowercase f is our frequency in cycles per second. We have pi, which is 3.14, and capital L, meaning inductance. So this is our formula for inductive reactance. In AC, this is an example. This comes right out of your textbook, the 8083. We have an AC circuit, an AC series circuit, in which the inductance is 0.146 Henry. The voltage is 110 volts AC. We have a frequency of 60 CPS. Inductive reactance is determined by the following method. So this is just a picture. This is the same information. We have our inductance. So here's our AC power, which we would have 110 volts. There's actually a better picture in your textbook that has this information listed on a drawing, but it looks just like this. So here we have our inductance. Our inductance is 0.14 Henry. We have our AC power, which is 110 volts, and we have our frequency of 60 CPS. So we plug in that information to our formula. We're trying to find inductive reactance. If we multiply 2 pi by our frequency, which is 60, and our inductance, represented by a capital L, which we were told is 0.146 Henry. We multiply all of that out and we get 55 for our inductive reactance, which is measured in ohms. So our inductive reactance of that circuit is 55 ohms. Now, we had talked about Ohm's law in DC circuits. So in AC circuits, we have something similar that we have to plug these numbers into to convert our information to a relationship with current and voltage. In any circuit where there is only resistance, the expression for the relationship of voltage and current is given by Ohm's law, which is current equals voltage over resistance. But when there is inductance in an AC circuit, the relationship between voltage and current is expressed as current equals voltage over reactance, which is symbolized by I equals E over XL. So if we want to find the current of that same circuit that we just found the reactance in, we would plug that into our formula. So this is like our Ohm's law formula for AC circuits where we're using inductive reactance. XL is our inductive reactance of the circuit in ohms. So remember our inductive reactance that we got was 55 ohms. So we have that here. Our voltage of that circuit was 110 volts AC, and we want to find our current. So if we are going to divide 110 volts by 55 ohms, that's going to give us 2 amps. So our current is 2 amps in that AC circuit. Okay. AC circuits in series. In AC series circuits, inductive reactances are added like resistances in series in a DC circuit. So I'm not going over any examples of series and parallel because the video that you guys watched for lecture in the last week. Covered a lot of examples of those. So this is just some information so that you guys have it to refer to when you're studying. So the total reactance in the circuit equals the sum of the individual reactances. And here's your formula for inductive reactance in series circuits. You have your inductive reactance represented by capital XL. So our total inductive reactance in a series circuit would come to your inductive reactance 1 plus inductive reactance 2 plus inductive reactance 3, and so on and so forth. And your inductive reactance in a parallel AC circuit. The total reactances of inductors connected in parallel is found the same way as the total resistance in a parallel DC circuit. The total reactance of inductances connected in parallel is expressed as, and you have your formula here. So you're also going to, you can see it in two different ways, similar to how you would see it with resistances. You may see 1 over your XL total equals 1 over XL1 plus 1 over XL2 plus 1 over XL3. I have it written here as you can plug it in as is and not have to transfer over the 1 over XLT. So here we have XL total, your inductive reactance total, equaling 1 over XL plus 1 over XL1 plus 1 over XL2 plus 1 over XL3, and so on and so forth. Okay, so this is just information so you guys can have it to refer to for studying, for formulas and such. But on your tests, the formulas will be provided, but I see a question here. It's not 1 over XLT in a parallel circuit. I'm not sure what you're asking, but here, let me type this in the chat, because you can also see this formula written as 1 over XLT, so your XL total equals 1 over XL1 plus 1 over XL2 plus 1 over XL3, and so on and so forth. Okay, so that is also the formula. They're the same thing. This is just written in a different way. So whatever information you have, you can plug it in to either formula. The difference being that the formula I typed in the chat, at the end of factoring all of this out, you will still need to transfer over the 1 on top of your inductive reactance total. Okay, yeah, so the slide does read, so the slide reads your inductive reactance total, and it puts the 1 over here, basically on the right side of your equation, instead of on the left side of your equation. So here. I'm going to add that in the slide just so that there's no confusion. But it is the same formula. It's just written with that extra step is basically factored in here for you. Okay, so I'm going to write it in here so that you guys aren't confused. Okay, so you will see that formula written like this. You can use it like this, or you can also use it. Run out of space here. Okay, or you will also see it like this. 1 over, I don't want to underline it, 1 over XL total equals 1 over XL1 plus 1 over XL2 plus 1 over XL3, so on and so forth. So either one of these equations is going to give you the same answer when you plug in the variables, okay? These are both the same equations, so don't get confused. It's just that the equation on the bottom, once you plug in all of your variables, a lot of people forget to divide out that 1 again and bring it over here, okay? So there you go. You have both of those formulas. Hopefully that will be a little, is that a little more clear? I think that you got it. It looks like it from the chat. So that's it. That's all we're going to go over in lecture today for inductance. A little more information for you guys to, okay, good. I see that that answered it. Thank you. I think that that'll make it more clear for everybody too. So you can use either one of those equations. They're really both the same. Just one of them has an extra step and one of them takes that step out for you. Just a matter of how you guys want to plug in the numbers. That's it for a lecture on inductance today. So some more information for you guys to review. I do want to tell you that there will be a quiz tonight. It will be open at 6. As usual, 5-question quiz. Okay, so make sure that you watch and review lecture prior to the quiz. Also, I don't know if you guys saw the announcement, but we will be, I posted the date for our final in this class. Let me pull it up. Okay, so we are going to be taking the final on, okay, so here I posted the announcement for the final in this class. The class final will be on Monday, December 7th. Okay, so here we are. It's the 16th. 1, 2, so 3 weeks. 3 weeks we have the final. It will open on Monday, December 7th, and it will close on Thursday, December 10th at midnight. Okay, so just mark your guys' calendars for that. I just want to make sure that you guys see that announcement is there. I will do a review for the final on Wednesday, December 2nd. That's what we will do for lecture. Your final is not going to be cumulative. It is only going to cover everything that we've discussed from the midterm through the end of the semester. Okay? So I'll talk more about that when we get to the final review on December 2nd. I just want to make you guys aware that that announcement is there. Okay, and that is it for lecture. If you have any other questions, you can type in the chat. Other than that, you'll see Mr. Kimball in lab tonight, and I will see you for lecture on Thursday. Thursday. Yeah. This Thursday, or I mean not Thursday, Wednesday, the 18th. Okay. Okay, thank you. Bye-bye.